Hello and welcome back. Today we're going to be discussing the theorem of linearity of limits. First, we have to define what linearity is. So, define the linear combination of f of x and g of x as follows. So, if we let c1 and c2 be some constants, some real constants, then a linear combination of f and g is the sum c1 times f of x plus c2 times g of x. In other words, we have a constant times f plus another constant times g. Now the theorem itself is a combination of two ideas. Again, let c1 and c2 be real constants. If the limit as x approaches x naught of f of x converges to L1 and the limit as x approaches x naught of g of x converges to L2, then the limit as x approaches x naught of the linear combination of f and g is equal to the c1 times the limit as x approaches x naught of f of x plus c2 times the limit as x approaches g of x, which is c1 times L1 plus c2 times L2. Basically what it's saying is that the limit of and let me just write this out here. What we're saying here is just that the limit of as x approaches x of some constant times f of x is equal to the constant times the limit x naught of f of x, and we're also saying that the limit as x approaches x naught of f of x plus g of x is equal to the limit of the sum of the limits. So we're just combining these two into one theorem. So it's important in breaking down limits into smaller pieces. Later we'll look at the product rule and, polynomials and all of that interesting things, and it'll really help us in computing such limits. But this is the theorem that we're going to be working with. So we're just going to combine it under one big umbrella. So let's prove this. We need to show that for all epsilon greater than 0, there exists a delta greater than 0 such that locally at x naught, so either that 0 less than the absolute value of, either 0 less than the absolute value of x minus x naught less than delta, or x is greater than delta, or x is less than minus delta. Either of these is true. Then this big thing, which we know this is what we have, that right there, is over here, and minus C1 L1, and this minus C2 L2, this is minus C1 L1 plus C2 L2, if you're wondering, is less than epsilon. So we're going to fix epsilon to be greater than 0. Let's write that out again. Less than epsilon. This is implied by we're going to try to group C1 f of x and C1 L1 and C2 g of x minus C2 L2. So what do we want to show? We want at the very end to get f of x minus L1 is less than a positive epsilon, and g of x minus L2 is less than another positive epsilon. And the reason for that is because if we can get these two statements to be true, then we're done, because we know these two statements are true locally at x naught by assumption, right? We assumed this to be true when we said that the limits of f and g were L1 and L2 respectively. So, in other words, if we get to that step, then we're done. We can just say that we finished our proof. So how are we going to get to that step? Well, we have to first group we have to group this over here and factor out C1. So notice we have C1 times the absolute value, the absolute value of C1 times the absolute value of fx minus L1 plus the absolute value of C2 times the absolute value of gx minus L2. And the reason why we group it, because now we have what we want, this and this. Now we just need to do another step. We could, in theory, just divide by C1 and get it. Okay, but first we would like split it into our epsilon over 2, and the other one less than epsilon over 2. We know how to do that. But we can't just simply end up over here. Over here, we can't simply end up dividing by C1 over here and dividing by C2 over here, because we don't cover the case if these constants are 0. I mean, we could do it, but then we'd have to do more cases, and casework is never a very smart option. So the efficient option in this case is just say the absolute value of C1 times the absolute value of f of x minus L1 is less than the absolute value of C1 plus 1 times the absolute value of f of x minus L1. The reason we're doing this is because this is always greater than or equal to 1, so it's always greater than 0, so it cannot be equal to 0, sorry. And we could use 2, we could use 3, really any number greater than 0 works. And we know that this left has to be less than the right because we're multiplying by a number greater than 1, like we just said, greater than or equal to 1. So we should actually right here, it would be more appropriate to write as well, or equal to, as well here, or equal to, because if they are 0, it could be equal to, but either way, we know that by writing this, we get rid of the possibility of it being 0, while also continuing down our proof, and we just let that to be epsilon over 2. Same thing with our other case right here. We also know that for C2 and g of x, this is less than the absolute value of C2 plus 1 times the absolute value of C2 plus 1 times the absolute value of g of x minus L2, which is less than epsilon over 2. That way now we can divide by this constant, and we know that epsilon over this number has to be, of course, a positive number. Same thing over here. And we know these are locally true at x naught by our hypothesis. So we got to this step, right? This is literally where we wanted to get. So we've now shown that whenever we have this case of f of x, as x approaches x naught of f of x is equal to L1 and the limit as x approaches x naught of g of x is equal to 2, then this linear combination is just the following right here. This is very helpful, and I'll show you an example. So compute with proof the limit as x approaches 5 of 3 times the square root of x minus 1 plus 5x squared. If we know that these limits are true, we can prove these limits to be true. We have enough tools to prove them, but I'm going to omit that step because that's really not necessary. It's kind of redundant, and we'll later show how to further compute these for radicals and for quadratics or polynomials. But we do know that this is true, and we can prove both of these if we wanted to with epsilon delta. Now, this, by the linearity of limits theorem, is just 3 times this limit plus 5 times this limit. So we split it. Very helpful, because we know that those limits are 3 times 4 plus 5 times 25, which is 137. So we have not only computed it, but we also found it. Here's a step where, if you remember, when I did my very first introduction to limits, I said, oh, we'll later prove tools to help us, like prove properties to help us remember how I said that the sum of limits is the limit of the sums, and vice versa, and also that the product of limits is the limit of the products. This is where we're getting to the point where we can actually prove these properties, and now we can actually show that this limit is actually what we're looking for. So on the AP exam, you will only be asked to compute a certain limit using these properties. So you do have to know properties. You do not have to know the name of the theorem. However, it is important to keep in mind that the proof, nevertheless, can also be very important. So hopefully this helped you out, and goodbye.